Bridges are some of the most remarkable feats of civil engineering. They are not only vital for connecting regions separated by bodies of water, mountains, or valleys, but also stand as symbols of human ingenuity, endurance, and technological progress. Building the world's longest bridges requires overcoming immense challenges. Designing structures that withstand natural forces, supporting heavy traffic loads, and lasting decades with minimal maintenance. Each long-span bridge represents a combination of advanced materials, construction innovations, and thorough planning. Among the longest bridges globally, 5 stand out for their scale, engineering solutions, and cultural or economic significance. These are the Lake Pontchartrain Causeway in the United States, the Bang Na Expressway in Thailand, the Donghai Bridge in China, the Vasco da Gama Bridge in Portugal, and the Penang Second Bridge in Malaysia. Each of these projects showcases how engineers adapt design and construction techniques to local geography, environmental challenges, and infrastructure needs. This video explores the technical details of these bridges, explaining their construction processes, the materials used, and their role in transportation and development. The Lake Pontchartrain Causeway, located in Louisiana, USA, is one of the most iconic bridges in the world. Stretching 38.4 kilometers, 23.8 miles, across Lake Pontchartrain, it held the Guinness World Record for the longest continuous bridge over water for decades. Completed in 1956, first span, and 1969, second span, the bridge remains a cornerstone of regional transportation. The bridge was constructed using precast, pre-stressed concrete segments supported on thousands of concrete pilings driven deep into the lake bed. More than 9,000 concrete piles, each averaging 55 feet, 16.7 meters long, were driven into soft sediments to create stable foundations. Engineers chose concrete over steel because of its durability in water environments and resistance to corrosion from the brackish lake. Construction crews used barges and cranes to transport and install the precast components. Since the lake is relatively shallow, average depth of about 12-14 feet, building from floating platforms was feasible. The bridge is composed of modular spans, each approximately 56 feet, 17 meters long, making assembly efficient. The modular approach also allowed for future expansions, which proved crucial when the second span was built parallel to the first. The biggest challenges included working over water, dealing with Louisiana's unpredictable weather, and ensuring safety during construction. Hurricanes were a constant threat, so engineers designed the bridge to withstand strong winds and waves. The alignment of the bridge required precise geotechnical surveys, as the lakebed sediments vary in depth and stability. The causeway connects New Orleans with the North Shore communities, dramatically reducing travel times. Its role extends beyond transportation. It serves as a lifeline during hurricanes, providing evacuation routes. Maintenance is a continuous process involving inspections of pilings and replacement of aging concrete segments. The Bang Na Expressway in Bangkok, Thailand, is one of the longest road bridges in the world, stretching 54 kilometers, 33.6 miles. Unlike traditional bridges spanning bodies of water, it is an elevated highway built primarily over existing roads and urban infrastructure. Completed in 2000, the project represented a new model of urban bridge construction. The bridge was constructed using the segmental box girder method, where precast concrete segments are assembled and joined using post-tensioning cables. This technique allowed engineers to build long spans with minimal disruption to the dense traffic below. The structure consists of 6 lanes, supported by thousands of piers spaced at intervals of about 30-40 meters. The use of precast, pre-stressed concrete ensured quick installation and uniform quality. To speed construction, factories were set up near the site to mass-produce concrete segments. These segments were then transported and lifted into place using specialized launching gantries. Bangkok's soft alluvial soil posed geotechnical challenges, as foundations had to be stable enough to support heavy loads. Engineers used deep pile foundations, some reaching depths of more than 40 meters to anchor the bridge. The tropical climate with heavy rains and high humidity also influenced material selection and construction schedules. Managing construction in a congested urban environment was another challenge. The bridge had to be built above existing roads without causing long-term traffic paralysis. Engineers adopted night shifts and carefully sequenced the installation of spans to minimize disruption. The Bang Na Expressway is a backbone of Bangkok's road system, reducing congestion and improving connectivity. It represents a hybrid between a bridge and an elevated highway, making it unique among the world's longest bridges. Economically, it boosted urban mobility, supported industrial growth, and became a model for large-scale infrastructure in developing megacities. The Donghai Bridge, completed in 2005, is a marvel of modern Chinese engineering. At 32.5 kilometers, 20.2 miles, it was China's first major sea-crossing bridge, linking Shanghai to the deep-water Yangshan port, part of the world's largest container port system. The Donghai Bridge was designed as a hybrid cable-stayed and beam bridge. It consists of long viaducts and a central cable-stayed section, with a main span of 420 meters, allowing large ships to pass underneath. The foundations were particularly complex due to the soft seabed sediments in Hangzhou Bay. Engineers drove thousands of steel and reinforced concrete piles deep into the seabed, some exceeding 70 meters in length, to secure the structure. The superstructure was built using high-strength pre-stressed concrete segments for the viaducts, while the cable-stayed section required steel pylons and cables to achieve the necessary span. Construction equipment such as floating cranes and large jack-up barges was essential for installing components in open water. The region's typhoons, high winds and waves created major challenges. The bridge had to be designed for extreme weather, including storm surges. The seismic risk in the Shanghai region also required advanced structural design. Engineers employed expansion joints and flexible connections to allow the bridge to move slightly without damage. The Donghai Bridge transformed Shanghai's logistics by directly connecting the city with Yangshan Port, which was built on offshore islands. It enabled massive growth in China's shipping and export capacity. Beyond its economic role, the bridge symbolizes China's rise in infrastructure and engineering capability. The Vasco da Gama Bridge in Lisbon, Portugal, is the longest bridge in Europe, stretching 17.2 kilometers, 10.7 miles, across the Tagus River. Completed in 1998 for Expo 98, the project was designed to relieve congestion on Lisbon's older 25 de Abril bridge. The bridge combines several structural forms: viaducts, cable-stayed spans, and access roads. The central cable-stayed section has a main span of 420 meters, designed to allow ship passage. The majority of the structure consists of viaducts built from precast concrete box girders, supported on piers. Foundations were challenging due to the soft, alluvial soils of the Tagus River estuary. Engineers used deep pile foundations, some reaching depths of 95 meters, making them among the deepest bridge foundations in Europe. The construction process involved the use of incremental launching methods for viaduct segments, where sections of the bridge deck were progressively pushed out over the piers. Large floating platforms and cranes supported operations in the river. Environmental concerns were a major factor. The Tagus estuary is an ecologically sensitive area, home to numerous bird species. Strict environmental regulations influenced the design and construction process, requiring measures to protect wildlife. Additionally, the bridge had to be designed to withstand earthquakes, as Lisbon lies in a seismic zone. Engineers incorporated flexibility into the structure, using seismic isolation bearings and expansion joints. The Vasco da Gama Bridge greatly improved Lisbon's transport network, relieving congestion and supporting urban expansion. It is also a striking architectural landmark, blending functionality with aesthetic appeal. The Penang Second Bridge, officially known as the Sultan Abdul Halim Muazzam Shah Bridge, is Southeast Asia's longest bridge, spanning 24 kilometers, 15 miles. Completed in 2014, it connects Penang Island with mainland Malaysia, easing traffic from the older Penang Bridge. The bridge is primarily a cable-stayed bridge with long viaduct sections. Its main span of 250 meters allows for ship navigation. The deck consists of precast concrete box girders, while the cable-stayed section uses high-strength steel cables anchored in pylons. Foundations required driving reinforced concrete piles deep into the seabed. Given the soft marine clay soils in the Penang Channel, some piles extended to depths of over 100 meters. Engineers employed advanced geotechnical monitoring to ensure stability. A unique aspect of construction was the use of incremental launching and balanced cantilever methods, which allowed for efficient assembly without disrupting shipping lanes. The Penang Channel is prone to strong tidal currents, posing difficulties for construction barges and cranes. Engineers designed the bridge to resist these forces, as well as seismic activity and tsunamis, which are regional risks. Environmental considerations were also important, as the area is home to fisheries and marine ecosystems. Mitigation measures included monitoring water quality and minimizing dredging impacts. The bridge boosted connectivity between Penang Island, an economic and cultural hub, and mainland Malaysia. It enhanced trade, tourism, and logistics while reducing traffic congestion on the older bridge. The project also highlighted Malaysia's ability to execute world-class infrastructure projects.